Hello, I'm Luke and this is Glenn, and we are talking about our new two-stroke bucket bike project. Had a lot of people asking some questions, so we figured we'd do a video, and Glenn's going to tell you all about it because he's the engineer behind it. And yeah, hopefully we answer some of your questions. So first of all, Glenn, what is it?
So we're calling it the TST100, which is just an acronym for two-stroke twin, 100cc. It's a bucket racer. Here in New Zealand, we run a class called bucket racing, or otherwise known as Formula 4. It's a grassroots motorsport class. It's cheap, and it leaves a lot of avenue for building really interesting stuff. Hence this motor, which is a custom-built 100cc.
So what are the rules of the class? Like what are we actually trying to achieve, and how does this fit into Formula 4 bucket racing?
Right, yeah, so the rules are 150cc 4-stroke, 100cc 2-stroke. You get some capacity limits for 2 strokes. You can go up to 110cc, you can stay water cooled, but you're 24mm carb limited. 125cc air cooled with a 24mm carb. So we've decided to fire this motor right into the 100cc bracket, which leaves our carburetor cross-section area open, and just I feel like in terms of performance potential that the 100cc 2-stroke, particularly the twin, is possibly one of the best options.
Yeah, and that, there's no cylinder limits in the rules, so you can make it a 40 cylinder if you wanted, like we were talking about earlier today. As many cylinders as you want. The bike just has to be based off of a road-going bike, so you can't have motocross engines or gearboxes or anything like that. So this is based off of an FZR 250 gearbox and clutch, and the whole back end of the motor, and then the cylinders and the cranks are based off of a Derby 50 scooter.
Yep, little moped scooter cylinders grafted onto a custom crankcase that houses a Yamaha FZR 250 gearbox clutch assembly. And the engine mounting point is the same as the FZR 250. So initially we were planning on putting it straight into a FZR 250 chassis because we've got a couple of them. That's changed, but even though that's changed, we're going to leave the engine mounts in the same position because it can.
Yeah, and then, if we ever did want to use this motor for something else, you can just bolt it straight into an FZR. The sprocket's in the same place as an FZR, the shifter's in the same place as an FZR. Bolt it straight in and it would go. Obviously, there's some carburetors and stuff like that you'd need to sort out yourself, but the idea being, if it's not broken, don't fix it, right? And we make this pretty universally usable, not just in this one bike that we're making. So why are we doing it, Glenn?
Why? Another one of our mates, Kyle, that's quite involved in this project. He's sort of honestly been a bit of the catalyst behind it. About a year ago, me and him were in the garage drinking beers, and he said we should turbo the little CBR 125 that he's got. Thought it'd be hilarious just to make some turbo noises, but it turns out it actually worked really well. And then that developed onto turboing a chopped in half FZR 250, so 125 twins, which will be sleeved down to 100. And that made great power, but it's horrible to ride. And so we're sort of starting to scratch around and going, well, we've learned some really interesting skills with the FZR 125 turbo that would apply to building a twin cylinder 100cc 2-stroke, which will hopefully perform really well in power, but actually be usable power. I think that's sort of where the project stemmed from, and then it's just become a real, the development of engineering tools now between 3D scanning, 3D printing, manufacturing techniques that just went around 10 years ago and now are seemingly extremely accessible. Again, in part to Kyle's input, he's the guru behind all the scanning and stuff like that. He's been the driving force with that. My engineering background allows me to model it and make it into a product or a project that we can actually build.
Yeah, so it opens heaps of doors where we can make stuff that you need a massive engineering firm to make 10 years ago. We can make a lot of that in the garage now. You can order 3D printed metal now, or even just the classic CNC. The 3D scanning makes the modeling on the computer a lot easier. I mean, you need someone like Glenn who has a lot of mechanical and engineering knowledge to be able to actually design something that's going to work. But yeah, we wanted to do it because ideally this thing is going to be the fastest bucket bike lap speed that, you know, has ever been built. That's the plan. Yeah, it's within the rules. It's going to make plenty of power. We're doing a custom chassis which should handle really good and be light. It's not just because it's going to be cool, although that's half the reason. It is because we want to go and break some lap records and you know, prove that we can build something competitive. Next question: who's doing it?
Yes.
Me, you, and Kyle.
Yeah. So at the moment, it's myself, yourself, and Kyle. It's the three of us idiots collectively putting our time and effort into to build something. I don't think I'd have the gumption to take it on purely on my own at the moment for the scale of project. It's too much work for a bucket. Just if I was just to do the whole thing off my own back. But yeah, it's just a cool group of people with wildly different skill sets that trying to integrate all of those different skill sets into an output.
Long term, we're thinking about building something a bit bigger than a bucket. So make all the mistakes on this one, learn all of the engineering skills and challenges that we need to learn so that we're not doing it on the big expensive project. And then eventually we go and build something a lot bigger and faster than a bucket bike.
Yep. Part of the project is developing sort of technology for ourselves. Controversially, I'm going to attempt to fuel inject it initially, which has been attempted particularly quite a lot of times and has been proven to be extremely difficult on a high performance small capacity two-stroke. If I can have success at fuel injecting this, then that opens the doors to larger cylinders being easier. You've got less revs and the injection system gives you more margin of error the bigger the cylinder gets. I've got some novel ideas that from what I can gather haven't been tried. Very basic, it's very on the face of it, fairly crude system compared to what's been tried, but it's an itch I have to scratch.
Yeah, and if it works, it's, you know.
Well, if it works, I can't wait to tell people about how it works. If it does work, it's extremely simple. It would make fuel injecting a two-stroke on par with the complexity of fuel injecting a four-stroke.
It's worth mentioning Glenn's just successfully fuel injected a turbo small capacity, 125cc twin cylinder four-stroke. So you're dealing with a few variables there. Small capacity, heaps of RPM. It's doing about 17,000 RPM. Boost, which is a variable. I think having done that successfully, you've learned a few things, and it lends itself for you to successfully fuel inject the two-stroke as well. Similar challenges. Yeah.
So there's some nuance to the two-stroke side, but some of the main problems that you chase with a small capacity two-stroke are the same. You've got expansion chamber. Think of an expansion chamber as a crude form of supercharging / turbocharging, where you get different fuel demand based on performance of the chamber, like a turbo on lag or not lag. And the big one is just the RPM, 18,000 RPM on a four-stroke. You're in the window now at least of trying to fuel inject a two-stroke at 14,000 RPM. It's still going to have its own challenges, and even to the point where ECU selection becomes really critical. Because obviously with a two-stroke you fire the plugs and injectors twice as often as you do on a four-stroke. So if you rev a two-stroke to 13,000 RPM, that'd be the four-stroke equivalent of a 26,000 RPM engine. Yeah, I could talk for hours on that.
Yeah. We'll do a bunch more videos throughout the build, showing what we've done and how we've done it. And this video will show you a bit of the design that Glenn's done, and then we're going to do a bit of dry fitting with some just 3D printed plastic engine cases, bit of a prototype before we make the aluminium. So Glenn, what's the end goal of the project? What are we trying to achieve?
Right, so we want it light, trying to keep weight down. So weight's the enemy of acceleration. Try to keep the thing sub 80 kilos. And all of this is trying to use really sort of cost-effective means. So the chassis is based off, not based, but uses Gixxer 150 parts. Wheel sets are the correct size wheels. They're okay in terms of their weight. We're using a tubular chassis to try to pull weight out, fiberglass tank, and keeping as much weight as possible out of the engine. The FZR 250 gearbox components are remarkably light for what they are. Some stuff about it's terrible, some stuff's good. Power, aiming for initially 30 horsepower, which is certainly not outside the realms of possibility with two 50cc engines combined. I think long term I'd have aspirations of quite a bit more than that, but if anything over 30 horsepower, consider a complete success. Really, probably the next step is utilising my background of road racing just to help dial in the chassis. Luke will be probably the prominent rider for this bike, and then go chase some lap records and do some GPs on it. And
I'm going to take it around the country and do a bit of racing on it, provided we get it running, which we haven't done yet. So this is all hypothetical, but I'm pretty confident that we'll get it going. I'm going to travel everywhere, showcase the bike, and ideally break lap records everywhere. This is Glenn and I at lap record pace at Kaitoki on FXR 150s. So ideally, we have a much better bike than an FXR 150, and going sub lap record shouldn't be too difficult. And then obviously, I don't know about any other tracks because I haven't ridden them yet, but we'll see. That's part of the end goal. We're doing it because it's cool, and it's going to sound ridiculous because it's 180-degree firing order, and it's going to do 4 million RPM. It should perform great. It should be fast lap speed. Not as fast in a straight line as the turbo FZR, but you don't have to wait for turbo lag. So
the challenge of riding a turbo bike cannot be overstated. Turbo might be fast, but it's awful. Whereas this should be responsive and reactive. Yeah,
direct, linear throttle application.
Yeah. And the fallback is on the fuel injection side is if it doesn't work, we put carburetors on it. That's the beauty with it. It's not we haven't specifically designed the engine, so I haven't designed myself into a corner with fuel injector locations and things where the carbs can't fit. It's as simple as having some traditional rubber manifolds and then your standard carbs just will bolt on, just like any twin cylinder 2-stroke. So from a design point, it's also something interesting is very little effort or energy has gone into designing the 2-stroke engine side. I had the luxury of purchasing really high quality good cylinders now for these engines off the shelf. We don't need to focus the energy on trying to develop a high performance 2-stroke. It's crankcase geometry, all of those things is just copy what works, which is what this engine is. The genius of this project is combining all of those parts that fit within the rules. That's the big part.
So you're allowed a custom crankcase, you can have a custom chassis, you just can't have a motocross engine or something dedicated for racing. This is all either off the shelf street bike parts or something Glenn's made. It's all within the rules. I'm sure there's some more ridiculous motors you could make that would fit within the rules, but this is pretty out there, I think. We were joking about making a 4-cylinder 2-stroke 100cc with 25cc cylinders, but we're kind of limited by nothing really exists that we can use. These cylinders you buy off the shelf, so it makes it a lot easier.
And they're extremely affordable too. Cylinder kit now, good quality cylinder kit, you're sort of looking at a few $100s in New Zealand. This would be an extraordinarily expensive engine if you were to include labour in it. But from a parts cost, we're talking in the same realm of what you would invest into a modified or set up FXR 150 engine. Maybe tens of thousands of dollars worth of labour, but it's a passion project.
So Glenn's going to take you through a lot of the CAD design, and then we're going to go and dry fit the motor.
This is the scan of the back half of the FZR 250 gearbox. Obviously with the front cut off because we don't care about any of that silly 4-stroke stuff. And you just do some simple geometries first to figure out where your centerline planes are of the crankcase joins. So you can see them there. And then get your centers of your shaft. So with the scanning, what you do is you get the scan's very accurate, but you want stuff like your centerline shaft center lines need to be bang on. So you measure those in the castings, and people are usually pretty smart and they do things to round numbers. So the gearbox shaft centers are 52 mil, so it gives you really nice numbers just to start with. And then show that. Just take a little bit to turn on. And then this is the light grey is my CAD drawing, and the dark grey is the 3D scan. So you can see bits of the FZR cases that we don't use for the horizontal bolt lines and stuff that are coming through. And then you can see we've got all our reed cage and all of this shit out the front. But where you get this hazing, where you can kind of see the scan poking through your model, this is how a great indication that you're getting really close. Like you can see there, you can see the facets of the scan are just sort of like hazing through, and that's how you judge that you're getting pretty close. So it was basically just copy the geometries, so you can see all of the hole geometries for the shift drum and everything. It's just copying that from the scan. And then once you kind of get all the geometries, you turn the scans off because they slow things down heaps while you're working in SolidWorks until you get to your finished engine. But if we go to the engine, we can sort of have a look at roughly how it's designed. So you start with a simple sketch here, which is called shaft center lines, and this just lays out where the crankshaft is in relationship to the two gearbox shafts. So they're you can't move those, you can't fight with them or do anything. And so I just started with a simple crankcase core. So this is where the two cranks will live with the bearings and seals and everything inside here. And then I went on to adding in the gearbox back half. So most of the geometry for most of the shape of the engine was driven by the clutch cover, the FZR 250 clutch cover geometry and engine mounts, because I wanted it to bolt into an FZR 250 chassis. And then it's just a case of just one piece at a time going through and adding the cuts and clearances and features and details that you need for each of the components. It starts off looking pretty boring, and then just one piece at a time, add them in. So there's all the cylinder bases and reed blocks and things. And then I go through a part called weight reduction, which is just cutting off material that doesn't need to be there, so adding in clearance through here. And the engine mount, stuff like that doesn't need to be solid, it can be machined out. Adding details for the clutch and the shifter. And eventually you just get to the point where you've added in all of the little details, bolt connections, everything. You can see this line here, and this line here is where the crankcases get split into their individual components. So that's just for access for machining, because we need to be able to get the tool in there to cut it out. And that's really the guts of the whole engine, really. And in here we still do some, so I did model up some rough parts. I did a rough model of the shift drum based off the true geometry, measuring it with a vernier, and then the shift rods, and also the gearbox. This is like an approximation of the gearbox just for clearance checking. And the beauty with SolidWorks is you can cut things in half and just have a look. So I can cut the gearbox in half, and then I can come down here and have a look at how the gear sits up in here and clearances for everything, make sure I'm not hitting anything, because I've had to do things quite different to how it's done from the factory because of it being a vertically split. But there's the one I noticed before that I kind of missed, that this clearance here is really tight, so I'll give that a little bit more clearance. Where are we? This is an assembly, so we can just add our parts in. So there's some dummy pistons, some reed blocks. So same thing with the reed blocks, it's great for being able to have a look at the geometry of the reeds as they enter the case. So we've got good clearance and good feed into there. One of the other things that's in here, which is a bit odd, is a picture of a Gixxer 150 chassis, because this is going to end up living in a high, well, it's not going to be a Gixxer 150 at all. It's using a Gixxer 150 wheel swing arm forks and headset into a custom design chassis, which I'll show you in a minute. The clutch will be using a KTM hydraulic slave. Super easy way of integrating a clutch actuation. Doing mechanical clutches is quite difficult, lots of parts to make and integrate, whereas this is just 3 bolt holes and then pushes on the clutch. And then come in here. So again with SolidWorks, I'm lucky enough to have a full fastener library, so I can add all my bolts in and check for bolt clearances and things like that. But right to the extent where I can look at the clearances for triggers, and I can move things around, so this is all geared together where I can move the pistons up and down. So you can see the crankshaft there. So it's fantastic for being able to do that. So you can actually go as far as setting all of your port timings and everything from within SolidWorks, which seems pretty crazy, but. And then finally, I think I just had it open with the FZR 250 clutch cover on it. And takes a little while to load. So 3D scans, the software just hates 3D scans, especially when you've got them high detail like what I'm using. All of the geometry for how the cylinders sit onto the base and everything, it's all driven from, or all derived from the 3D scans. Yeah, that's about it really. Alright, so here's the overview of the engine setting and what will be the customized chassis for it, using some of the Gixxer 150 parts. The tank, 3D scan of a Honda NSR 250 tank with just a generic bucket racing tail fairing, which is based on RS125. But this gives a great show of how good the scanning is. This the Honda and the wing that you can see, that's not from an image, that's the thickness of the vinyl graphic on the fuel tank I scanned that you can see. So we're talking 0.1 of a millimeter accuracy on the scans, which is just insane. I'll just turn the tank and the tail fairing off. I'm going to talk through some of the chassis. So the chassis is fully custom, but using the locations of the standard Gixxer 150 swing arm. So this is a copy. This is the Gixxer 150 swing arm with some tubular braces added to give some stiffness, but the shock position, everything about this main structure is unmodified. It's reasonably lightweight for what it is. It's fairly thin walled, and the forks and offset and everything are based on the Gixxer 150, which is, they work out pretty good. We've got 23-degree headset angle with 88 millimeters trail, which is pretty good for a bucket, and we're 1280 mil wheelbase, which I think somewhere around the 1300 to me is the best balance of turning radius and stability of bike. Kaitaki's not a fast track, but there's a couple of corners there. It makes a big difference to lap speed if you can get through there with a stable bike. So turn 1 particularly, which is wide open throttle usually. But the chassis it's as simple as I could possibly make it. At the moment, I haven't done a bolt-on subframe, so the subframe is just simply part of the frame, and even the rear sets I've just done as tubular rear sets, which are part of the frame. My thinking being is, we don't carry spare rear sets of buckets anyway, so if you've really torched them up that bad, you're either making something new and custom because nothing's going to fit, or otherwise it's cut that off and weld a couple more tubes on, same amount of work. So we'll try those out and see if it works. The design of the chassis is based around how easy it is to make. It's the biggest driving force in it. There's still a few little braces that I'll add. I think I'll do some triangulation on the engine mount. And that's about it for the chassis. We've got some pipes in there which are roughly drawn up at the moment. Beauty with 50cc cylinders is the pipes are tiny, so they package in there really easy. Probably won't leave them side mounted like that maybe. I'll probably just bring the mufflers up to the side. And yeah, it's the easy part done, now we've got to make it.
Off you go.
Assembling the two-stroke twin. Not the first time, second time. But we'll chuck it together and show you how the whole thing works. This is the 3D printed crankcases test fitting. FZR 250 gearbox, shifter drum, all that. And then these are our Derby 50 cylinders. FZR clutch, everything. Drive gear off FZR crank, which will mesh into the clutch, and throttle bodies. So all of the biggest challenge with putting the FZR 250 gearbox into this engine design is the FZR cases. They're split horizontally, so everything's designed to drop in from the top, apart from the shift drum. Whereas we've done, for manufacturing reasons, we've got vertically split cases, so it's a bit more of a trick to get everything in, but so far it does seem to work.
How much work did it save you to have the 3D the 3D laser scan to like get the shift drum in the right place and all of that?
Hours and hours and hours.
Yeah, because you just copied the...
Yeah, so all of the geometry for where the shift drum location is and shift fork, everything is purely derived off the 3D scan. I did a couple of check dimensions with the vernier to kind of make sure I was in the ballpark, but the 3D scan now is so accurate, it's 0.1 of a mil, that if you get, with the location of shift shafts and stuff like that, they're just a cast piece, you know, they're not super accurate.
Yeah.
If you're within 0.1 of a mil, that it's
more than enough.
The gearbox will tolerate it. Probably the single biggest part of moving this project forward is being able to use 3D scanning to get all this geometry.
Yeah, because otherwise, I mean, look at the complexity of that FZR casing.
Yeah, that's right. And there's so many parts that are all interacting in here. I mean, this is, you can see where I've ground out there. There was a cock up in the design because it didn't have metal here, and I just thought it was just for oil to pass through, but it's not. It's actually a clearance for the shift fork.
Yeah.
You know, so that's the beauty again with now 3D printing it in plastic. I can just get the Dremel out in 10 seconds. So this is where it gets tricky with installing what should be a horizontally dropped-in gearbox into a vertical engine. I mean, to be honest with you, it's not really much difference than if you were doing a normal vertically split gearbox. They sometimes have to sort of wiggle in together to get them all going.
That's a bit more like, you know, your typical bucket bike engine, like in FXR.
Yeah, correct. Yeah. It's just a little bit more fiddly. I mean, I've obviously done this a few times now with it, so I know how it likes.
Yeah, because the FXR gearbox is designed to do it, rather than this one isn't.
Yeah, that's right. Yeah, like getting all of these little retainer plates for like the shift drum. Like imagine having to model up every single piece of that as you're going.
Oh,
and
yeah.
get it right and make sure your holes are lining up, you know, whereas I just go, cool.
Take the laser scan model,
just
throw it in.
just draw a hole over the hole in SolidWorks and call it done.
It's so much easier.
Yeah, it's insane. And this is really, you know, like the 3D scanner that Kyle organise and understands all the background of it. I know how to use things. He knows how to make them work on that front.
The software.
So yeah, the software, and just like it's a little fiddly at first. So it's a little bit of a learning curve as you first get it to figure out how to import it, and handle the mesh inside SolidWorks, and
Yeah.
it's just a new bit. But in terms of like the scanning, you know, like I feel it was probably 10 years ago since I really spent, probably close to 10 years ago that I really spent a lot of time in SolidWorks working on engine related stuff. It would have been when I was doing the 300 two-stroke. And like this shit just didn't exist back then.
Yeah.
You know, you couldn't.
It's amazing what you can do now, even in the last few years, like you say.
Yeah, there you go. That's we're neutral.
Working gearbox.
That's it. That's the gearbox.
And you were saying you're not running an oil pump in this motor.
No oil pump. So don't really need an oil pump in a race bike like this, especially a low horsepower bike like this. The splash of the lubrication of the oil just bouncing around as you hit the brakes and things like that's more than enough. You just have to make sure that you keep your oil level high enough that some oil will splash onto the gears. Road bikes, they have to run oil pumps in the gearboxes because if you're cruising along 100k an hour, zero acceleration, the oil settles out, and then the gears aren't running in oil, and eventually they'll kill bearings. Like motocross bikes don't have oil pumps because obviously getting all bounced around with oil. I mean, some of the 4-strokes they have an oil pump, so they'll oil the gear, but the 2-stroke always a 125 doesn't. So
and that's never a problem.
Yeah, so next part will be we don't have bearings or anything yet for the crank, but so we have one crank live like this. These shafts here get cut short, and then there's a coupler that picks up on the keys and then orientates the crank. Crank's 180 degrees out, and that all lives inside that hole there, and that's how the two cranks talk to each other. But we don't have any bearings or the couplers or anything at the moment, so I won't bother putting that crank in. Yeah, well, we were talking about, you know, the potential idea of using a PA6 with carbon fibre reinforcement as an actual engine case. But that's a project for another day.
Yeah, we'll finish the first one first.
Again, just picks up on all of the factory geometries. Gets through the gears.
That's so cool, eh?
That's pretty neat, eh? So there's a few little custom parts that have to be made because of the changes of how this engine is assembled. I have to have, like in this engine here, it uses a snap ring to locate the bearing for the clutch. And this, I don't get this. I have to have a this face here basically to capture it. So I'm going to have to manufacture some special washers, hardened washers. It's just a plastic temporary one that'll sit in there and just keep the clutch hub off that new face. This is kind of the weird part of this engine, I guess. Now is using the FZR clutch. You can see it's got this huge ring gear, which is completely unnecessary for this engine. Like, it doesn't need this final drive, but this is path of least resistance. I've got 4 of these gearboxes floating around, and they're really close ratio gearbox, and it works out that the 50cc will rev to 15,000 RPM, which is sort of in the ballpark of what the FZR power range is. So the gearing and everything is going to work out pretty close. So this here will get cut up and machined, so it goes onto the end of the crank, and then that's your drive for your clutch.
Nice.
Pretty simple. So all of this is just, like you see, you know, if this was built in aluminium, it's just assembling any.
It seems, to be honest, like it goes together easier than a lot of motors I've seen.
Yeah, I mean, it's a two-stroke, so it is by nature, you know, basic.
Yeah.
So there's, I didn't point it out, there's a couple of holes through the two case halves to
Allow for oil movement.
just to allow the oil from basically the clutch side into that side. You know, it's plastic gearbox.
Yeah.
So yeah, no, yeah, obviously the case has been split. So normally with an engine you'd have two halves, but this is kind of three main parts of cases that'll be doweled together. And that's just for manufacturing, just simply so you can get a tool in here to machine this out, tool in there to machine that out. Because if you try to do it in two pieces through the middle, then you just can't manufacture it. Not with traditional machining.
And you've designed it to be specifically applicable for CNC milling.
Yeah. So
the billet.
I did. The intention was to try 3D print it in aluminium, because that's what I really want to try. But it's still, the price has come down heaps, but it's still just way too cost prohibitive to think about.
Not worth it for a bucket bike.
So there you go, just to save some manufacturing, use the FZR 250 clutch cover on it. I need to reinvent the wheel when we've already got all the geometry of the clutch basket in there. So yeah, and same with the engine mounts, all FZR 250. So this motor, if we didn't put it into a sort of custom chassis, can bolt directly into an FZR 250 chassis. Which is a suitable size chassis, because even though it's a 100cc twin, it's actually still really wide. Like these cylinders are huge.
Yeah.
They're massive, like they're bigger than a YZ125 cylinder. So yeah, obviously no bearings in here. This is the crank just sitting in the crankcase, but gives you an idea of how it all goes together. And then I actually have to clearance these. I pushed them as close together as I practically could. And I knew that I was going to have to. I just need to file a tiny bit of material off each of the heads there. Reeds. Drop them like that. We haven't got them made yet, but some throttle bodies, some adapters to put the throttle bodies in, which will just be straight shots like that. And this will have two sets of injectors. There'll be an injector here, which is sort of your slow speed running injector, and then there'll also be a shower injector over each one. Yeah, and then crank trigger goes there. That's the pickup sensor there, and
that's a TST 100.
there you go. That's a TST 100. Simple as.
I mean, you've done the head on wrong.
Oh, I got it on backwards, mate. There we go.
Cool.
All of these strange dots are from 3D scanning. If anyone's wondering. So it's a bit of a gawky looking motor. I didn't spend a lot of time on sort of cosmetics of it. Everything is there because it needs to be there. So it very much looks like I slapped another engine onto the side of the engine. This bit here sort of hangs out the side.
That output shaft, is that in exactly the same spot as relative to the engine mounts as the FZR 250?
Correct. Yeah, and same with the shift lever.
Yeah, so you could bolt it into an FZR 250 chassis and run the same shifter, same
Shift setup,
chain,
everything.
and
So
it's got the same anti-squat, everything.
Everything. engine mount, all geometry, like all critical geometries to the motor and the chassis are identical. Not that we'll probably run it in an FZR chassis now, but it's a,
if you wanted to. And if someone
to.
wanted one of these motors and, and you were feeling kind to build them one.
Yeah, well, that's it. But yeah, the 3D printing is amazing for like the little things you forget. Like I forgot to put an oil drain in it to get the, you know, like worst case scenario is if you did, it's got a oil filler because the filler's on the clutch cap.
Yeah.
You know, so the worst case scenario is you'd have to take the clutch cover off to drain oil.
Yeah,
so it's not
turn it on its side.
Yeah, it's not like the end of the world, but it's here's the opportunity to capture all of this shit and figure it out.
Cool, 24 minutes, engine assembled.
Yeah, chuck it in the bike and fire it up, mate.
Can.